So the first one is I take full responsibility. I only showed you one example in the notes on how to do this. Okay, but basically, if it's being asked to figure out um, if events are independent versus dependent, like if it's just like that, if they give you, you want to check. You're like, well, if things are independent, then event A and event B, right, should technically be probability of the first event times probability of the second event. And because you don't have that, given that in this example and this formula, right, this is saying, hey, this is when events are independent, meaning this event does not affect that one, right? So you are given both. So both tests getting above 70 or higher is right there. So what I will do is I plug in that for here. So I'm going to go 0.2852 is equal to, right, probability of both happening. I put it on the left hand side, and on the right hand side, I need my different highlighters there. I'm going to figure out the probability of the first event is 0.62. And the probability of the second event is 0.46. Right? 0.46 right there. And 0.62 is right there. So I'm checking to see if the left-hand side is equal to right-hand side. Okay, so basically all the math is happening on this side here. So what you get is 0.2852 when you multiply these two. And we can put the same, we can just copy that, right? And then you conclude, okay, so if they are indeed equal, right, left-hand side is equal to right-hand side, therefore events are independent. So if you're given probabilities, you can actually mathematically calculate that. If it's just like, let's say I give you a story, and you're like, hey, are these events dependent or independent? What do you think? So when there is something that, right, tossing a coin and rolling a die, events are independent, right? But if you're taking cards from a deck and you're not replacing it, that should be ding, ding, ding. That should be, hey, these events are dependent. Why is that? Because things are not being replaced, so one event affects the second. And so next, in a bag of 80 chips, 2 will be defective. If you draw 2 chips without replacing them, very important, right? That is being said. What is the probability that both chips are defective, or both chips are not defective? So this is basically saying probability of D&D, Dungeons and Dragons, and not D&D. That's basically what this is saying, right? Find both of them. So because things are not being replaced, I'm going to figure out the defective. So at first I have 2 out of 80 that are defective. And then because I drew that one and I'm not replacing it, there's 1 out of 79. There we go. Plus, probability of not being defective, well, you kind of reset, right? You forget this. Okay, now let's look at that second scenario. 78 out of 80 times 77 out of 79, right? So these are the probabilities. So 1 times 2 is 2. 80 times 79 is 6320. Plus 78 times 77 is 6006 over same denominator, right? That's why I don't like to simplify either, because it's easier than in this case to add, right? So if you add these, you get 6008 out of 6320, which is 0.9503. Okay, so that's the probability of that happening. By the way, you could have done a tree diagram. These are both ends of that tree diagram, but if you go to the top, right, if you follow the top branch, that's both effective. if you were to follow the bottom branches, you get both not effective. There's stuff in between, and that's why it's only 0.95, right? It's not 100%. So nice to do this on a Monday morning, right? Cheers you up. I feel your pain, guys. I feel your pain. I'm trying my best here. Okay, this one you should recognize this. There'll be at least one on the test like this. At least one, right? There's one for sure waiting for you there. So if you remember to set the alarm, 82% chance you'll be on time. You should forget there's a 25% of being on time. Remember, suppose you remember to set your alarm 75% of the time, draw a tree diagram. So setting the alarm is what precedes everything. So alarm, not alarm. So that'd be 0.75, 0.25. And then you got late, not late, late, not late, right? So something happens if you set the alarm, then there, do you do time not on time? It's up to you what you want to do. I will do time not on time. Sorry, just to avoid confusion here. Or time late, right? How's that? I prefer that. Okay, go for it. On time is 0.82. Late, therefore, is the difference, right? 0.18. And if you forget to set the alarm, there's only a 0.25% chance of being on time. Therefore, there's a 0.75, right? So these add up to 1 individually. And then I want you to do this, okay? Doesn't take a long time. Alarm and on time, alarm and late, probability of alarm not setting it and being on time, probability of forgetting to set the alarm and being late, okay? So do this, and you can just multiply them. You don't need to show me that you're multiplying them. You just go this times this is 0.615, and then this times this is 0.135, 0.0625, and 0.1875. Okay? So this, if you do this right, these should add up to 1, right? Okay, do a quick check, and that's what you're getting there. And then I will probably ask you questions based on that. Are we good so far? Go ahead. Go ahead. And then we have, what's the probability you will be on time as a percent to 2 decimal places? Very picky, right? Anyways, probability of being on time. So probability of time, just being on time. So you just check, right? This one and this one does the trick, right? So show me the 2 that you're adding. Because even if you get it wrong, like let's say you make a mistake on the diagram, I will still give you the marks for consistency here. Okay, so you get 0.6775, 67.75%, right? To probability of just being on time at any given day, putting together all these variables, that's the probability of you being on time. Okay, whether you forget or not, if you combine all those probabilities, that is on any given day, this is the chances of you being on time. Okay, because things are depending on each other. Next. This one is the trickiest one of all. A question like this. So maybe I'm going to give you I'm going to give it one last try to get you to understand this. What's the probability that you remember to set your alarm clock given that you're not on time? So figure out the given when you see given, or considering the fact that this happened. Let's write it out real quickly. Probability that you remember to set the alarm given that you were late. That's what this question is asking right there. Figure out that one. Figure out that one. That's what they're asking. So let's go back to the formula. We would most definitely say we're relating alarm and being late. Those are the 2 that we're considering here. This is always the second thing that we write down. Right? The given that always as the second part of the formula. So what goes here? What already happened? The given, right? Like the late, right? This happened, and then now you're trying to figure out what's the probability of setting the alarm given that you were late. So it's almost LOL, right? LAL, but that's a pattern. Like this given part is what comes first. Okay, and then you just go get your numbers. This is way up there. Sorry, 0.615. Probably being late. You just calculated. No, you didn't calculate that. Probably being late. We'll do this. Watch this. We're gonna have to go up and figure out. There you're late, 0.135, and you're also late right there. This one right there. So I have to put that in brackets. I have to add it up. If we had done it here, okay, then you just use that number, plug it in. But here we have to actually do that. We have to add up the probabilities of being late. And this I just call X, this part right here. One more line, 0.615, this is going to be tight. This adds up to 0.3225x. And now what's the last thing we do? Divide both sides by. I think I made a mistake. Because you can't have this has to be bigger than that. Do you see the mistake? I see it. How about this? I give you a bonus mark if you figure out my mistake. This is the mistake here. Setting an alarm and late. I grabbed alarm and on time, right? I grabbed that one. I have to grab this one. Okay, so I have to grab 0.135. This is how you know you made a mistake. If this number that you're going to divide both by, if that number is smaller than that, you made a mistake. So let's fix this right here. It's 135. 135, 135. There you go. Now it's fixed. Now we're going to divide both sides by 0.3225. Okay, so this turns into 1, right? So x is equal to 0.4186. So that's the probability, right, of having set your alarm given that you are late. On any given day, if you're late, right, on any given day, there's a 41.86% chance that you set the alarm. So watch the mistake I just made there. It can happen to you. So it's just like you're about to divide, you're like, wait a minute. If this is bigger than what you're dividing by, you're going to get a probability that's greater than 100%. That cannot be. Okay. Okay, backside. Here we have question 4. Coin is tossed 3 times. Find the probability of getting at least 2 heads. I don't know. You might have tails, heads, right? Tail. A lot of you did this. And by the way, dependent, independent events, your tree diagrams can be used every single time if you understand what's happening. So we have tail, 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 heads, tail, heads, tails, tails, heads, heads, and then we've got heads, tails, tails, heads, tails, heads, sorry, heads, heads, tail, and all heads, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8 outcomes, which is what you expected, right? You've got 2 options for the first toss, 2 for the second, 2 for the third, so that's 8 options, right, or outcomes. Okay, you've got 8 outcomes, this makes sense. So you want at least 2, so you just go highlight or circle 2 heads, right? So at least 2. So there, no, there. So there's four instances, 4 out of 8, which is 1/2. All that work just for that, right? Two cards are drawn from the top of a well-shuffled deck. What's the probability that they are both aces, black aces, sorry. So whether you want to look at it as grabbing two at the same time or grabbing one at a time, it gives you the same answer, okay? So you've got 2 black aces at the beginning and 1 black ace on that second, right? So that's 2 over 2652. I will be very specific on the test. I won't leave it up for like, what we have. I'll say you grab one, then you grab another one, and maybe a third one, but you're grabbing them one at a time. Did anybody use combinations here? You got the same answer? Yeah. So that's fine. If you use combinations, so you go out of 2, choose 2 over, out of 52, choose 2, right? All right, get the same answer. This is just 1 over, it's going to be a reduced fraction. What's the denominator? Yeah, I actually knew that, but I'm too nervous on a Monday. I don't want to get it wrong. There we go. So either way, if you want to look at it as doing both at the time or one at a time, it doesn't matter. But these are dependent events. Okay. Oop, I just gave it away. A die is thrown twice, so it's a probability both numbers are prime. Do you know your prime numbers? It can only be divided by 1 and itself. So here, 2, 3, 5, 7, 11, 13. Like if you know the first couple, you're fine. Maybe study sheet entry. Optimus Prime. Did I hear that on the background there? So how many primes can you have on a die? 2, 3, 5, right? Right? Oh, sorry. I don't think 1 is a prime. As a math teacher, I should know this, right? I think it's a long debated. I won't have primes on the test. How is that? You can handle that, right? So we've got 3 out of 6 times 3 out of 6. So it's half, half, right? Half times half, which is a quarter. Here. What does it say? What does Google? No. Google says no. Isn't that nice? Like sometimes you Google something and it's just, I don't know. Somebody says this. I like to just know, right? Go up. Because they're independent events, right? If I tossed it 100 times, it'd be 1/2 to the power of 100, right? And then you get your probability there. Yeah. How about this? If it doesn't say anything, you assume it's a 6-sided. But I will be more specific. A bag contains marbles. Marble questions. Okay, so there's 5, 4, and 1. That's 10. Just gonna make a note there. Marbles chosen at random, not replaced. Okay, right? Very important. Dependent events. Then a second marble is chosen. What's the probability that neither is blue? So you want probability of not blue and not blue. And so not blue would be 9 out of 10, the first draw, right? And then it's 8 out of 9 for the second. Hey, this is a good, this 9 and that 9, right? 9 goes into both ones. Like if things are multiplying like that, you can do it. 2 goes in here 4 times, 2 goes in there 5 times. So it's 4 out of 5. You got that anyways, right? You got, if you turn that into a decimal, you got 0.8. Okay. A code consists of 2-digit numbers chosen from 0 00 to 99, followed by 2 letters. What's the probability of getting this code? Well, you need your universal. The universal would be 1, 2, 3, 4. So you've got 2 numbers. So you've got 10 times 10, right? And then letters, 26 times 26. Nope. Can you? It doesn't say if you can or cannot repeat. 2 different letters. Never mind. 2 different letters. Voila, right? Like that's so tricky. So this has to be 25. It doesn't say numbers. It doesn't give us any restrictions on that. So you've got 65,000 options there. So what's the probability of getting this specific one? How many codes like this would there be? There's only one. That's your probability there. It's like winning the lottery, right? There's only one right answer. There's only one plate of that. If they give you a specific example, there's only one, right? There's only one. So question 3 was dependent. Question 4, independent. That's the coin. Question 5, let's see. That's dependent because you're grabbing one at a time, or even if you grab both of them, but it's one affects the other. 6, die, that's independent. So that's that. For tomorrow, for the test, there will be one cumulative, which is a surface area question, surface area volume, one of those of a composite shape. So, right, I'm combining things. So surface area volume, just remember to review that a little bit. What's that? You keep it. Yeah, I call this a mock quiz.